Differential equations. Objectives. By this lesson, you should be able to define and recognize a differential equation, solve a differential equation with or without an initial condition, understand the applications of differential equations in a variety of settings. Start with some definitions. So a differential equation just means an equation that involves derivatives, right? Simple. Initial condition, a condition or set conditions on a solution to a differential equation that will allow you to find a particular solution. That's just a value they give you to say, hey, when you find this, use this to find a particular value. One example of this would be if they gave you y of 1 equals 2. So all they're saying here is, hey, when the x value is 1, you get 2. Or when you substitute 1 for x, you get 2 for the y. The general solution to a differential equation is the most general form of a solution and doesn't take account initial conditions. So this is before you plug in your initial condition, you have a general solution. And a lot of times you might just leave it like that. Sometimes you actually have to you have to use the initial condition to find what we call a solution. And a solution, right? Solution to a differential equation, a specific solution that not only satisfies the differential equation but also satisfies the given initial condition. So the general idea is we're gonna do an operation. Sometimes you have an initial condition. If you do, then we're gonna use that to find our solution. If you don't, a lot of times just leave it in the general solution form. So what the sets are solving. So it's actually not as bad as it looks. Sets are solving a differential equation. Gather the same variables on opposite sides of the equal sign. So all that means is this. Right, if I have something like dy dx equals, 2x plus 1, I want to put the dx on that side. Right, I want all the same variables, all the dx's to be on one side, all the y's to be on the other side. That's the first step. We're going to separate. And then we're going to integrate both sides with respect to the appropriate variable. That's why we need dx on that side. So when we integrate this guy, we're going to have a dx there to let us know, A, integrate with respect to x. Although both sides are indefinite integrals, we yield a general constant. So after you integrate, you have to put a plus c. You don't put it on both sides, you just put it on one side. Because it takes care. Like if you had a constant on both sides, you just combine them. Just subtract one from both sides. From each side. If provided initial condition, use it to solve for c, and then substitute your c back in to solve an explicitly for the dependent variable y. That just means after you find your solution, plug c back in, so you have an actual nice value for y. So let's do a quick example. So step 1 here. We're going to multiply both sides by dx because we want to put the x's on the other side. So I'm going to get dy equals 3x squared dx. Right, so again, I want to solve this, give my initial condition y is 0 equals 2. Now that I have that, I can integrate both sides. Integral of dy, it's like a 1 there. The integral of 1 is this y. Equals the integral of the side, add 1 to the power, divide by a new power. X cubed. Now, remember, I got to add a constant somewhere. You got to add either side. We like to add the side with the x in it. So that's my general solution. But now I'm going to use my initial condition. So we're going to plug this in. Now remember, this is my x and this is my y. So they're saying when I plug in 0 for x, I get 2. So this tells me that c is 2. And then we're going to rewrite it. Y equals x cubed plus 2. And that's that's solving a differential equation with the initial condition. So let's do a couple more. Right, same thing here. Now remember, I cannot just integrate it first because integrating this side would be a mess. It's dy over dx. We don't know how to do that. So first you gotta move the dx to both sides. So we're gonna get dy equals 4x to the 7th dx. I'm gonna go a little faster this time. Integrate both sides. Integral 1 is this y. Integral this side, add 1 to the power divided by new power. I get 1/2, 4 over 8, x to the 8th, plus c. And again, that plus c can go on either side. It's just easier to put on the x side. And then, let's find our c. Let's sub this guy in there. So when I plug in 0 for x, I get 4 for my y. They're not always going to be this easy. So 4 equals c, rewrite it, y equals 1/2 x to the 8th plus 4. So this is the next one. Now notice the next one's written a little differently, right? It's y prime equals sine pi t given y of 2 equals 2. So I have another initial condition. So I'm going to rewrite this for the sake of us so you can see what's going on. Remember, y prime is the same thing as saying dx, dy dx. And then just like we always do, I'm gonna multiply dx to both sides. Again, I show way more work than I expect you to. And now I can integrate both sides. On this side I get y. On this side, that is a, we haven't talked about this in detail yet, but it's what we're going to call a reverse chain rule. It's going to be cosine. General sign is negative cosine actually. Pi t times 1 over pi. We'll talk about that more later. Plus c. So that's my equation, and then I got to solve for c. So we're going to sub in our initial condition, and I get 2 equals negative cosine of 2 pi times 1 over pi plus c. Cosine of 2 pi, little trig. Here's cosine. That point is 0, 1. Right, cosine x, sine e, sine y. So this is just 0. So 2 equals 0. 0 times n equals 0 plus c. So c equals 2. Sub it back in. And plus 2. And that's my differential equation. So the next one I'm going to do a little slightly different for my next one here. Instead of rewriting y prime as dy dx and then moving the dx over, I'm going to write it like this. So we know that y equals the integral of y prime, right? So if I integrate this guy, I get y. That's by definition. Well, we know y prime equals this, so I can just write it like this. Then apply dx here. I know we don't write it, but it's implied. So instead of integrating both sides, instead of rewriting this, I'm going to essentially integrate both sides. So I get this. And then we integrate like we know how to integrate. Now, at 10, you can pull it out if you want. It's 10 integral of e to negative 2x dx. This is a reverse chain rule. In a reverse chain, take the integral of the outside. E is just e, leave the inside alone. And then divide by the derivative of the inside. Right, so reverse chain rule, just for a little review, is you integrate the outside. We usually cast out integration as a capital letter, leave the inside alone, and then 1 over the derivative of the inside. So a little reverse chain rule there. Where am I at? I forgot my 10 and a plus c. So I get that. Simplify that a little bit. 10 and the negative 1/2, I get y equals negative 5e to the negative 2x plus c. And I have no initial condition, so this is my general solution, right? Normally, if I have an initial condition, I'll plug it in to find my c. But in this case, there's none, so I'm just going to leave my answer like that. So the next one. We're almost done. So this one, I'm trying to do a little curveball. They have y double prime, and then they have an initial condition on y prime. So other than that, we do it the exact same way. I write this as, I'm essentially integrate both sides. Not technically, but it's the same thing. So that's going to be the integral of 3x plus 2 dx. And then we just integrate that, add 1 to the power, divide by new power, add dx. So my y prime equals 3x squared over 2 plus 2x plus c. Now, to find my c, use the initial condition. So when I sub in 0 for x, my y should be 1. My y prime should be 1 in this case. I get 1 equals c. So I can rewrite my equation as y prime equals 3x squared over 2 plus 2x plus 1. There we go. Right, so it works same way no matter what the derivative is. Oh, we have the third derivative, integrate the second derivative, right? We have second derivative here, we integrate it as an initial condition for the first derivative. So it still works. And the last problem we're doing here today, let's try an application problem. At time t equals 0, a car traveling with velocity of 96 feet per second begins to slow down. The constant deceleration of a equals negative 12 feet per second squared. Find the velocity at time t, and distance traveled before the car comes to a halt, right, before it stops. So first, let's write down what we have. At time equals 0, my velocity is 96 feet per second. So velocity equals 96 feet per second. That's a little misleading. What's actually going on is this, right? They're saying when time is 0, my velocity equals 96 feet per second. So they're actually giving us an initial condition, right? It's not. This makes it look like an equation. It's actually this, right? When I sub in 0 for my x, my velocity is 96 feet per second. For my time, actually my t in this case. So that's an initial condition I have. And I actually have an equation here. They actually give me an equation. They tell me, hey, the acceleration is negative 12 feet per second squared. Remember the way we do SVA? Displacement, velocity, acceleration. So we have this equation. I want to get to velocity. I want to find the velocity equation. So to go up, we integrate. So let's integrate this equation. So the integral of acceleration is velocity. In that case, that'll be the integral of negative 12. Integral of negative 12, you just add the variable. In this case, we're talking about t. So this is negative 12t plus c. Don't forget to add the constant. So that's my equation. Now let's find out what c is. Just plug in my initial condition. So it says when I plug in 0, I get 96. So 96 equals negative 12 times 0 plus c. So 96 equals c. So my velocity equation is this. Feet per second. So there's find the velocity of v of t at time t. So that's my particular solution to that equation. Now let's look at the other equation. The other question, sorry. The distance traveled, we gotta find the distance traveled before the car comes to a halt. Now it has to do with displacement. Distance traveled is displacement. The only problem here is that, yeah, I can integrate it. I can integrate velocity again to get displacement, but I don't have an initial condition. They don't give me any value here. So we gotta think about, is there a way I could think about it? Well, let's read that question again. Distance traveled before the car comes to a halt. So it's a little funky, but they haven't started tracking the car's movement yet until we actually start. So my initial displacement is just going to be 0. Because we're saying, hey, we're going to start at a certain time, and we're going to see how long it takes us to end. So no matter where I start, I don't care where it is, we're going to consider it at 0. We just want to figure out how long it takes to stop. So it's a little tricky, but that's my initial condition. F of 0 is 0, because we just want to figure out how long it takes to stop. Now stopping, remember a little review. When is a particle at rest? When the velocity equals 0. So we're going to use both of these to solve this. So first, let's come up with the displacement equation. So we have to integrate this to get my displacement equation. The integration of velocity is displacement. That is the wrong type of s. There we go. That's equal to the integral of this guy. So if we integrate this, we're going to add 1 to the power, divide by a new power. I'll just add a t here. So it's negative 6t squared plus 96t plus c. That's my displacement. And now I'm gonna plug in my initial condition. Now my 0, 0. And again, why is that? Because we haven't started counting yet. We just want to figure out how long the car takes to stop. So wherever we start, that's our new 0. So again, a little weird, but that's the way it goes. So we're gonna plug in 0, 0. Find my c. You figure out already. You don't even do no math. All this is 0. I get c equals 0. So my equation for displacement is just this. That's my displacement equation. Now we want to figure out the distance traveled before the car comes to a halt. Remember, coming to a halt means that the car comes to a stop. So that means the velocity equals 0. So you gotta figure out when the velocity equals 0 so you can figure out a time when the car is at stops. So remember, here was our velocity equation. Ignore the integration signs. So you want to figure out when the velocity equals 0. So we're gonna set that equation equal to 0. So we're gonna get 1296 equals 12t, and then divide by 12, and we get t equals 8 seconds, right? Time. So that's when the car comes to halt, 8 seconds. How long has it traveled? Well, let's sub it in. So s of 8 equals negative 6, 8 squared plus 96 times 8, and that would give us I'd use a calculator for we get this, and then if you add them, you get 384 feet. So it takes 284 feet to come to a stop, and that's the lesson.